All right, good morning, chemists. So this is our last day. Let's not be sad that it's over, but happy that we've made it this far. So I won't be making any big announcements or anything. I'll save that. I'll make an announcement this afternoon on Canvas because I want to save time for getting through the rest of our nuclear chemistry slides, focusing on what's going to be on the final exam, talk about some cool aspects of nuclear chemistry as well, do some demos, blow some stuff up, and have an inspirational send-off. I'm still trying to come up with the right words, so let's see if it comes together. So typically I like to share a word cloud with all of my chemistry classes, so all of you submitted things you think of when I say the word chemistry, and so here are all of your responses. And so I like to do this every year. They look really similar every year. We have obviously atoms, chemicals, elements. That's what you think of when you think of the word chemistry. We have some other words here like difficult, pain, challenging, and those words are absolutely all right as well because in life we encounter a lot of different obstacles. But hopefully we can use the skills that we've learned along the way within our life to overcome those obstacles. So I always like to share this word cloud. There's some I like in here, chickens, and whatever Gibby is. I'm assuming Gibbs free energy, just like a cute Gibbs free energy type thing. All right, so I'll put that in the announcement so you can have that forever. If you were in my 1210 class, you'll see they look exactly the same. They look exactly the same every year. But I always enjoy looking at what you guys say. All right, so you might, over here, there's this weird piece of wood making its way around the class that people are okay, it's over there. Is the pen still with it? Yeah, okay. So a non-zero number of students have asked me why I carry a piece of wood with me to all my classes, and the reason is because I'm cheap. And I like ergonomics too. So I need something to elevate my iPad. I was about to use real money to buy something, all right, to elevate my iPad so I could teach better, but I'm cheap, and so I just grabbed a piece of wood out of the scrap pile and have been using this exact piece of wood for, I don't know, like 2 years now. And I mentioned to a student, hey, maybe I'll let you guys sign it at the end of the year. But the thing is I like my piece of wood, all right, that I use. So I just grabbed a different piece of wood out of the scrap pile and I'll have all of you guys sign it. And so they're actually wood planks from my house. And so I just cut them up into pieces, but I like the tongue and groove on it so I can stack them in my office. And then maybe one day when I retire, I can have a full wall of a bunch of signatures of all of my different classes. So I have a different piece of wood for my 1250 class. So I think that's kind of maybe a tradition I'll start. I don't know if you think that's cool. So that's making its way around the class. So if you want, you don't have to sign it, but I'd appreciate it. If you lose the pen, I have more pens. I'll be here, after class. You can sign it after class for the people up there, and I'll bring it to office hours, so you can sign it during office hours as well. All right, so let's finish nuclear chemistry. All right, we were talking about different types of radiation. So we already talked about alpha particles, beta, what? Okay, alpha particles, beta particles, gamma rays. So you see that gamma rays are not on this list because gamma rays, there's no mass. So gamma is not a particle, it's just pure energy. So it's not on the list, but I do have it on the side here as well. And so we'll talk about some less common decay processes that transform substances into something else. But before I do that, I'll do a demonstration. Unfortunately, I can't do any nuclear chemistry. I can't do any, fission or fusion reactions, but I can show you, sources of radiation in our everyday life. All right, so I have a Geiger counter here, and it just senses different types of radiation. So it can be alpha or beta particles. So I have some samples here. So this is sodium chloride. I'll just tell you that it does not emit radiation or does not undergo any nuclear decay processes, and I can prove that to you right now. So we have to be a little bit quiet because you hear the beep, beep, beeps. All right, so we gotta be a little quiet to hear the beep, beep, beeps. Okay, so there's very little beep, beeps. You hear it. Why are you recording this? Okay, all right, so here is sodium chloride. Now I have uranium. All right, yes, I have uranium. So do we think that this will make it go beep, beep, beep? Yes, it will, so come on. I do have to make you. Yes, uranium does undergo decay processes. Now something a little less common, sodium iodide. So iodine. Iodine also undergoes nuclear decay processes as well. It's an alpha emitter. So we can see a little bit of beep, beep, beep as well, or hear it at least, for sodium iodide. There we go. Okay, so these things, so let's go back to uranium because there's a lot of beeps. Uranium is an alpha emitter, so I have here a lead sheet. Do alpha particles go through lead? No, yeah, so in one of the other slides we talk about the penetrating power of like alpha and beta particles. So here you hear the beep, beep, beeps, okay, of uranium, but if I put a lead shield behind it, oh, come on. It's supposed to not, there we go. See? All right, there we go. So there's less beep, beep, beeps because the alpha particles are not penetrating the lead shield. I gave the demo lab an old smoke detector to see if we couldn't, sense the alpha particles that come off the americium-241 that we talked about on Tuesday. But unfortunately, we couldn't get it to work. I asked the demo lab to just destroy it and hit it with a hammer to try to get the radioactive source, but they're working on it. We don't know if it's gonna work. And we'll sense the alpha particles, but we'll see. I kind of did it. I went to Angie and I was like, can we do a demo off the books? And she's like, of course we can. So we'll see if that works. Maybe it'll come out, maybe it'll work, we'll see. All right. Okay, so let's talk about less common decay processes. So we'll just go through here. Positron emission. So a positron is just you can think like in a positively charged electron. It has very little mass, which is why there's a zero mass number, and it's a positive charge. And so we oftentimes give it the symbol E, because you want to think of it like just a positively charged electron, or sometimes they use the beta symbol, but the difference is that it's a positive charge and not the negative charge like the beta particles we talked about previously. So this is positron emission. So when we do a balanced chemical reaction, where do we want to put that positron? If it's emission, as a product, yes, because it's being emitted. So if a positron is involved in your chemical reaction, put it as a product and just balance those mass numbers and protons appropriately. So when a substance undergoes positron emission, what happens is that a proton can spontaneously emit its positive charge, essentially rendering it a neutron. So it just loses its positive charge. So therefore we change the identity because you're losing a proton, and you get that positron. So here's my positron. I don't have the positive charge on there. +1, there's our positron. All right, and so we render that proton, it becomes a neutron. The identity changes. So here's an example. Potassium-40 is a positron emitter, and so you see that the positron is a product. So I like to just balance the mass numbers and number of protons here. So the mass number of the product has to be 40, and then what is the number of protons then of my product? It has to be 18, yes. And so we look at the periodic table and we see that potassium now becomes argon. Interesting, yes, argon. All right, so even the potassium, there's naturally occurring potassium-40 in everything, all right, all living things. So like even bananas, high in potassium, does have a small amount of potassium-40, which undergoes positron emission and becomes argon. So yeah, if I brought the Geiger counter to the banana, you might hear some beep, beep, beeps as well because of its positron emission. All right, so there's positrons. They turn protons into neutrons when one's emitted. And then the last type of decay process is electron capture. All right, so see how the wording here changes? Your substance is capturing an electron, so think of it as being absorbed. So therefore, our electron is what? A product or a reactant. Now it's a reactant. And so these electrons are being captured by the nucleus. So this is different than other types of chemical changes we've talked about, like electron affinity. That just has to do with, our, fluffy electron shell. This is an electron being captured into the nucleus. That negative charge of the electron changes the identity of a proton. And so we see, if we add up these numbers, if we add up those numbers, the mass number of my product is what? 1. And then what is the number of protons of my product? 0. And what is that? That is a neutron. Yes, because there's no charge and it's all mass. All right, so this is interesting. Positron emission and electron capture, they both result in the formation of a neutron. The process is a little bit different here, where either an electron is captured or a positron is emitted. Both of them result in the same substance produced. And kind of to prove it to you, let's do electron capture of potassium-40. And think about what that product would be. So electron capture, remember the numbers and the charges for an electron. So it's going to be 0 and -1, that's my electron. And so the mass numbers and stuff for my product have to be 40. And then what's the number of protons? 18, what is that? Argon. Interesting, so it looks like, yeah, both electron capture and positron emission, if it's the same substance undergoing that process, the product is the same. Interesting. Okay. All right. So, So this slide is kind of a summary of all the different decay modes we just talked about. And so, my strategy here is just understand what an alpha particle is. Okay, alpha particle, mass number 4, 2 protons. It's typically a product. So you just add up those numbers appropriately to figure out what substance is missing in order to keep the mass number and protons mass balanced. Again, we don't care about electrons balancing charge when doing nuclear reactions. Beta decay, this is typically a product, and so again, as long as you understand what a beta particle is, you can balance things appropriately. And so we see that these two decay processes, the overall net change of your substance, you see that Z, our number of protons, does in fact change for our substances. Either the number of proton decreases by 2 or by 1. So we see that the atomic number, the identity of your substance, actually changes with alpha and beta decay. We don't see that with gamma because gamma is just pure energy. And so we see, zeros, you'll just get the same substance, just more stable. So we don't change the identity of our thing. And then the last two we talked about, positron emission, electron capture. Do note where those substances are in the balanced chemical equation. Positron is a product in emission, and electron capture, it's a reactant. But we get the exact same kind of net change happening for positron emission and electron capture. All right, so there we go. So that kind of summarizes things. So now let's put this into the context of substances that we see or we don't see off of the periodic table. So, why do some substances undergo nuclear decay processes? There's some reasoning for it, and it's less grounded in thermodynamics than the rest of this course has been. So there are some rules for nuclear stability, and it kind of seems almost arbitrary. I'm not an expert in nuclear chemistry, so besides these slides and these rules, just understand that this is just based upon the observations we see in substances that are on our periodic table. So nuclear stability, so these are the atoms we actually see in real life on Earth. Typically, I guess the number one rule is the largest, most stable nucleus is bismuth. That anything heavier than bismuth, so bismuth I think is like 82 protons, all right? Anything that has more than 82 protons, so 83 and above, those are all unstable, all of them. So if you look at the periodic table, any element past bismuth, we see the mass numbers, or like the molar masses, are in parentheses, meaning that they are not stable. They don't exist long enough to have a natural abundance with, decimal places. You look, anything, 80, oh no, bismuth is 83, sorry. Yeah. Okay, anything above 80, so 83, anything above 84. Oh, I have it right there, what the heck? Okay, so anything above 84, sorry, is not stable. So we see PO, which is 84 protons, again, in parentheses because they're not stable. And anything heavier than that, all have parentheses. Okay, all unstable. Yeah. 91 and 92, where is that? 91 and 92. Oh, because there's enough of it, so like uranium and stuff, they are unstable, that they do exist long enough to, they still are not stable, they still undergo, so like uranium undergoes nuclear decay processes, but we know enough about uranium that we can calculate a natural abundance and calculate a molar mass. But for the most part, most of those heavier elements, we see those parentheses, they're not stable enough to actually have a molar mass. All right, so largest is bismuth. Everything else will undergo nuclear decay processes to become something else until it's stable. That's the big idea. The second rule, and this is, I don't really like this rule. They call it magic numbers. Chemistry is not magic. It's not magic. And I'm glad that no one, I don't think on the word cloud said magic when thinking about chemistry, because everything in chemistry is explainable, either through thermodynamics or whatever. So I don't like that they use the term magic numbers, but basically, again, this is based upon observations that they saw that with certain number of protons and neutrons, those elements, those isotopes tend to be more stable. And so those magic numbers are 2, 8, 20, and etc. And so any nuclei that has like these number of protons or neutrons just tend to be more stable. We see more of those in real life on Earth. All right, and so some examples I have here. So if we calculate the number of protons or neutrons, we can see that these isotopes tend to be more stable, and we see a lot of it on Earth. So helium has how many protons? 2. I even tell you that in the corner there. And so therefore has 2 neutrons to have that mass number of 4. And so we see, oh, helium actually has a doubly magic number because there's 2 protons and 2 neutrons. So it's doubly magic. And so, so helium 4 is extremely stable. I don't like this reasoning, okay, just with magic numbers. All right, oxygen has what, 8 protons, 8 neutrons, and so we see oxygen has double magic numbers, so we see that oxygen 16 is an extremely stable nuclei. And you can tell from its its atomic mass on the periodic table, see how like oxygen is basically exactly 16. It's like 16.0000 whatever, because like 99.999% of oxygen atoms are oxygen 16 because of this doubly magic thing. All right, calcium is something like 20 and 20. And again, 20 is a magic number as well. So we see calcium 40 is in fact extremely stable. Lead, on the other hand, so lead has 82 protons. I can't do that math. How many neutrons are there? I don't know. 208 minus 82. 126, there we go. So does lead have double magic numbers? No? Are you sure? 82 and 126. Yeah, so lead 208 is extremely stable as well. So what we see here is, when we have like uranium or other heavy elements that undergo nuclear decay processes, most of their nuclear decay chains end with lead. All right, that they'll keep decaying until they reach lead 208, which is extremely stable. Okay, there we go. So that one is stable. All of these are double magic numbers. All right, and then the last one here, that's supposed to be a 3, which is interesting, and again, based upon observations, is that nuclei with even number of protons tend to just be more stable than nuclei that have odd number of protons. So here's just kind of a graph showcasing that if we added up all of the stable isotopes that have even number of protons and neutrons, there are 157 different elements with isotopes with both even numbers. And so there's 157 versus stable isotopes that have 2 odd number of protons and neutrons. There's only 5 of them. Right? So even numbers just tend to be more stable. You can see this based upon the periodic table also. Elements with 2 or fewer stable isotopes, those are mostly the odd number of atomic numbers, versus these red ones or pink ones, elements with 3 or more stable isotopes, those are all the even number atomic number ones. And so that, again, a lot of these rules are just based upon observations that we see of stable nuclei on Earth. Okay, so those are stability rules. So now we can apply them and think, okay, you know, if we have an unstable nuclei, what kind of decay process happens? So these are the patterns for nuclear stability. So if a substance is unstable, there is a strategy to calculate what kind of decay process happens. So we saw that alpha, beta, positron emission, all of those decay processes result in the change in identity of the substance. That change usually forces that substance to go in a direction that makes it more stable. So let's look at the different patterns. So again, patterns are based upon observations we see. So this graph here in the corner shows you all these blue dots are stable nuclei that we find on Earth. These yellow ones are unstable nuclei that tend to undergo nuclear decay processes. So what we see here is this trend. So on the y-axis is number of neutrons in your nucleus versus number of protons in your nucleus. So we see that the ratio, this neutron to proton ratio, tends to be a set number for stable nuclei. So if we can calculate the neutron to proton ratio for certain nuclei and ask ourselves, are we above this belt of stability or below the belt of stability, we can predict what happens. So what happens here is that for really light elements, so elements that are usually like lighter than calcium or something, they tend to have neutron to proton ratios of 1, meaning that there's the same number of protons and neutrons. So those are for lighter elements. So I like to kind of cap that at like calcium 40, which has 20 and 20. So its neutron to proton ratio would be 1. So for those light elements, if their neutron to proton ratio is 1, they are stable, they will not undergo nuclear decay processes. But if your nuclear decay process is anywhere above or below that, then it will undergo nuclear decay. All right, so that's for light elements, and what we see also as elements start to get heavier and heavier, the point that you want stable nuclei, that neutron to proton ratio tends to increase. So here are just kind of some like save points for us. Like for example, our stable iron isotope, its neutron to proton ratio is 1.15. When we get even heavier iodine, it's actually 1.4. And then all the way up to bismuth, our last stable isotope is 1.25. So there's almost 1.5 neutrons for every proton in a stable bismuth atom. You know these guys, and you know these balloons. It's nothing new, nothing new. All right, so now that we know where the belt of stability is, these are our stable isotopes. Our neutron to proton ratio tends to increase for heavier elements. Now let's ask ourselves does it work? Yeah. It works? Mm-hmm. Okay, it works? Okay, so Angie, this is the innards of a smoke detector. And Angie says that it works. All right, because smoke detectors do contain an alpha emitter, americium-241. Am I pronouncing that right?
I have no idea.
Okay, great. Okay, great. All right, it's an alpha emitter. So let's see. Does it work?
Yeah.
Okay.
So
how do you do it?
you point it at it like this.
Okay.
I swear I got it to work.
You got it to work?
I did. I got it to work on him.
Just a little radioactive.
Yes. Come on.
No.
No. Does it beep?
It only beeps once. It doesn't beep like the Geiger counter.
Can you do it on the Geiger counter? Yeah, go grab the Geiger counter.
You're seeing science in real time.
I know.
She appeared at my door and was holding a smoke detector, and I was like, oh.
Yeah, I said, let's
That's
do a
a
demo.
great
Let's
idea.
do a demo off the books.
Yeah, no, it was, so it's measuring in millisieverts, and it was working before. Put it on the point one.
Oh. Oh.
Well, sometimes it's background.
Come on.
Okay, try it on the.
Might have to break it more, Angie. Okay. There was a beep. Maybe.
Try you.
Oh.
Try you. Yeah.
No.
No,
Yeah.
You gotta check the background because we're all a little bit radioactive.
There we go. Yay! Smoke detector. Yeah.
Can I keep this?
Oh yeah, absolutely. I don't want a broken smoke detector.
Why?
Okay. All right. Yeah, so americium-241 is an alpha emitter. Angie gains a smoke detector. Okay, great. Oh, she put it in the wrong order. All right. So what if we're not on the belt of stability? Okay, we calculate the neutron to proton ratio. If we're not on the belt of stability, this is what happens. If we are above the belt, meaning that your neutron to proton ratio is like way above 1, typically what happens is beta emission because it converts a neutron to a proton. And so let's think about that numerically. If we convert a neutron to a proton, we change that neutron to proton ratio n-1, p + 1. We see that the neutron to proton ratio will go down. So we can go down the belt, like, move our way down. Let's say we're here and we move our way down, so we're closer to the belt of stability where those blue dots are, right? That's if we're way above the neutron to proton ratio. Versus if we're below the belt, all right? If we're below the belt, say that we're like let's say we're like right here, where we calculate the neutron to proton ratio, we don't have enough neutrons. What happens? Positron emission happens, or electron capture, because it's the same, you yield the same product. And so if we do electron capture or positron emission, it converts a proton to a neutron. So we add 1 to our neutron count, but subtract 1 from our proton count. And so how does that NP ratio change? It goes up. All right, and so that's how we go to our belt of stability. All right, so if we're above the belt, we do beta emission. If we're below the belt, we do positron emission, and that's how we go up. Now, the last piece is the third type of nuclear decay process is alpha emission. So alpha emission tends to happen when we have elements that are way, way heavier than bismuth, because we already said anything heavier than bismuth will always undergo nuclear decay. So if we're like over here, all right, I'll do a different color. If we're over here, way above the number of protons of bismuth, we don't want to go up or down the belt of stability. We actually want to go diagonally towards where those blue dots are. And so alpha emission will do that because we subtract 4 from we lose 2 neutrons and we lose 2 protons. So we see that the N to P ratio, right, N-2, P-2, that we move diagonally towards the belt of stability. So those are the rules. So I like to think, okay, if we're above 83, alpha emission. I would just memorize that, okay? I think I have it here, yes, just memorize this. This is the strategy. You will have alpha emission if you have more than, let's do a different color, more than 83 protons. You will always undergo alpha emission. Okay. Beta emission if what? We are above, below? Above the belt. Yes, if we are above the belt of our neutron to proton ratio, if it's way too high. And then the last one, we typically have positron emission if we are below the belt, or N to P ratio. All right, so let's put that to action. So let's think about carbon-14. Carbon-12 is the most stable nuclei, all right, of carbon, all right? That's why our molar mass for carbon is like 12.01. It's mostly carbon-12. So let's calculate the neutron to proton ratio of carbon. Carbon has 6 protons, right? Yep. How many neutrons? 8. So its N to P ratio is something like 1.33, okay? So just based upon that number, carbon's fairly light. Are we above or below the belt of stability? We're quite obviously above the belt because one, carbon is light. So what is like the preferred neutron to proton ratio? It should be 1. So 1.3 is obviously way too big. So what kind of decay process is going to happen? Beta, yes, beta emission. Okay, great. All right, what about calcium-38? So calcium-38 has 20 protons, yep, and then it has 18 neutrons. So its neutron to proton ratio is what? It's less than 1, 18 divided by 20, but if we want an actual number, it is 0.9. So where are we, above or below the belt? Below, yes, we're below the belt, so what's gonna happen? We're going to do positron emission, positron. Okay, and then the last one is uranium here. So uranium, we could go ahead and calculate the neutron to proton ratio, but do we really have to? No, because uranium falls under what category? Uranium has 92 protons, so it has to undergo alpha emission because it's heavier than bismuth. So we really don't need to calculate N to P for that one. All right. Okay, so, and what we see here, let's do it for calcium. So if we do beta emission for calcium, all right, so a beta particle is 0, -1, and let's think about the product that's made there. So calcium is 20 protons. So calcium, when it undergoes beta emission, is going to make 38, and what does it become? What's that beta particle? What is that, 21? Okay, so, and it's not calcium anymore. Now what is it? It is scantium, yes. So let's calculate the new neutron to proton ratio for this new product and see if we can get closer to the belts of stability. So scantium has 21 protons, and then how many neutrons? 38 minus 21, 17. Oh, wait. Oh, sorry. That's a beta. I did beta emission. That's why you're all giggling. Okay. Sorry. Yes, that didn't make sense to me either. All right. Sorry. There is positron emission. So what do we make? Yeah, we make potassium. So 19, 38. There we go. That makes more sense. We make potassium. Yeah, we did this one already. So potassium, if we calculate its neutron to proton ratio, is 19 protons over, 19 neutrons. Yay. Look. So when we did positron emission, and we made potassium 38, we were able to get its neutron to proton ratio to increase up to 1. So now it is stable. Okay, great. All right, so let's do this last one because this is how like the exam questions are worded. Which of the following nuclei is most likely to decay by positron emission? So I like to think, okay, what's the criteria for positron emission? Its N to P ratio has to be low. Yeah, so that's what we have to do. We need to calculate the neutron to proton ratio for all of these. So, so number of protons for these. So chromium is what? 24. Manganese is 25. And iron is 26. Okay, so now I need the number of neutrons where the mass numbers are given here. So 53 minus 24 is 29. Manganese, 21. 51 minus 24 is 27. And iron is 59 minus 26 is 33. So we do N over P, so 29 over 24. We see that the chromium isotope given has a N to P ratio of 1.2. Manganese, 27 over 24. What did I do wrong? Oh no. And did I do one wrong? Yeah. Oh no. Oh no. Okay. Okay, we'll do this. We'll do this. We'll do this. Frickin' technology on the last day. I need to get through these slides. Go. Change source. Ops. Go, go, go. It works? Okay, there we go. All right, perfect. All right. What did I do wrong? What is manganese? 20 what? 25. Okay. So then I calculated that wrong. So 51 minus 25 is 26. There we go. All right, that makes more sense. So 26 divided by 25 is 1.04, and then iron 33 divided by 26 is 1.23. So we see that manganese does in fact have the lowest neutron to proton ratio. Yes, it's above 1, but remember the stable neutron to proton ratio does tend to increase from 1 as we get heavier and heavier. So the indicator here is that manganese has the lowest, this isotope has the lowest neutron to proton ratio, so it's most likely to have positron emission. Great. All right. So, radioactive series. So I mentioned that all really heavy nuclei, anything above bismuth, will always undergo some type of decay to become something else until it is stable. So, you know, in like nuclear energy, nuclear power plants, we're typically using uranium, the fission process of uranium, and taking into account uranium's decay process. That uranium, because it has 92 protons, will spontaneously convert to something else until it is stable. So the nuclear decay chain for certain radioactive substances above bismuth typically follow a very particular pattern until it creates a stable nucleus. So here's an example of what uranium-238 undergoes in order to become a stable nuclei. This lead, what is that, like 206 stable nuclei. So for example, this radioactive series or decay chain for uranium-38 is first it'll undergo an alpha emission, then beta, then beta, then alpha. So it's not a learning objective for you to memorize the decay chain. What is a learning objective is if I tell you uranium-238 undergoes alpha, beta, beta, alpha, tell me what product is made. All right, what transformation has happened? And so really all this is just balancing subsequent, a bunch of reactions that take place. And again, so understanding that a alpha particle has a mass number of 4 and 2 protons, that's gonna help you figure out what you make. Beta is 0 and -1. Beta is 0 and -1. Alpha is 4 and 2. So we just need to think about what product do we have to make everything balanced. All right, so if this alpha particle is emitted, I like to just write the numbers to make everything balanced. What's the mass number of my new product? 234, right? And then how many protons are in that product? Oh, I didn't tell you what uranium is. It's 92. 92, right? So what's the number of protons? 90, yes, because remember, alpha is emitted, it has to be a product. So this particle plus whatever product I make have to add up to whatever the numbers are for uranium, right? And then you can see what element that is. It is thorium. Is thorium radioactive? Yes, because it is above 83, yes. So it's still gonna keep decaying. So what happens next? Beta decay, all right? So what's the mass number for beta decay? So 234 again, because beta particles don't have mass, but they do have charge. So our proton is gonna emit, a neutron is gonna emit a beta particle, and so we see that the number of protons has to be 91. So what do we make? PA, whatever that is. All right. And so that's kind of interesting. You know, we like made our way down the periodic table, but now we're going back up, which is interesting. All right. And it's, again, part of a series. Eventually, it will become a stable nuclei. All right. So then what's next? Another beta emission. So 234, and then we make our way up to 92 again. Oh, now we're freaking back at uranium. Interesting. All right, interesting. But it's a different isotope of uranium, right? And now we'll make our way down the chain again with another alpha emission. So to balance that, it's 230 and then 90. So now we have thorium again. So that would be the process of those particular steps of the chain. So we only made our way, I think, to here. And of course, we see from this graph, there's more alpha emissions that happen, some more betas, some alphas, and then eventually we get to lead, the stable form of lead. And then that's the end of the decay series, right? So uranium does not undergo radioactive decay straight to a stable nuclei. It happens in a lot of little steps. And that's the big idea there, right? And so again, don't memorize the decay chain. Just understand that uranium, lots of steps to get to lead, but we could ask you, okay, if we undergo a bunch of different nuclear decays, eventually we will, what nuclei is predicted to come off of those steps of the chain. All right, that's the radioactive series. Okay, so the last bit here, we just looked at substances spontaneously emitting radiation. So we looked at just radioactive substances that either emit an alpha or beta particle, whatever, but part of nuclear chemistry as well, making new substances, we are in fact making new elements, is atom smashing, where we can smash two atoms together, combine their nuclei to make new substances. So this is called transmutations because we're taking two substances and making some other substance. These balancing reactions, they work exactly the same as previous, like our previous mass numbers and protons and stuff. The only difference is that we're combining different nuclei to make new nuclei. So here's an example. If I take a neon atom and I throw an alpha particle at it, one of the products is an oxygen atom, but we can predict what does the other product have to be as well. So it's kind of interesting here. We're shoving together two nuclei and getting one or two out. So if we see neon here, if we add up things, I like to just take the sum. So we have 24 is our mass number and 12 is our number of protons. I just think, okay, my two products have to add up to those two numbers. So what are the numbers for my product? It has to be 8 and 4. What is that? What is it? Beryllium. Yay. Cool. So yeah, smashing a alpha particle to a neon particle, we get oxygen and beryllium. Cool. And I would have to give you what one of them is, all right, in order for you to balance it. Because you can't, like me, I couldn't even tell you that these are the two products you get. We have to give you one of them. All right, and then the last one here, so if I smash two neon atoms together, let's take the sum of the reactant side, 40, 20, we get an oxygen atom, a gamma ray, which is, again, 0 mass number, 0 charge, so that's not contributing to the numbers at all. So we can just kind of think here, if I do that subtraction, 20, 24 and 12, what is that? What is it? Magnesium, cool. All right, so smashing two neon atoms, we get an oxygen and a magnesium and a butt ton of energy. All right, and so this is what happens in particle accelerators, all right, in CERN over in Europe, where they have this big elliptical, almost like a racetrack type thing, but it's huge. It's so big it encompasses multiple countries, right, where it's a racetrack that they just accelerate particles really, really, really fast to get it to have enough kinetic energy, where then we can smash two atoms together to transmute them into other things. And so here is an example. Here's the picture of CERN, or the Large Hadron Collider. It's right here. And there's some other particle accelerators too over in Europe. And then they talked about building a new particle accelerator. This encompasses like way more countries, but I don't think this ever came to fruition. Yes, unfortunately. But that's, the Large Hadron Collider does in fact exist, and they do atom smashing there. Okay, making new stuff. Okay, all right. So that is the second to last learning objective for nuclear chemistry that's on the exam. The last one is rates of nuclear reactions. But the thing is you already know how to do all of it, okay? This is basically chapter 14 review, because I might have mentioned it when we did chapter 14, but all radioactive decay processes follow first order kinetics. Do you remember first order kinetics? No? Well, you better. All right, so this should be review. All right, that when we talked about kinetics, we had rate laws. So if this is first order, the rate of your reaction just depends on the concentration of the one species. And so the one species is the substance that's undergoing decay. And so we have rate laws, but more importantly, what we use to do calculations and stuff is the integrated rate law. All right, remember the integrated rate law? That the natural log of the concentration at some time is equal to the initial, natural log of the initial concentration of your stuff minus the rate constant times the time that has elapsed. And so that's our integrated rate law. We can calculate, given an amount of time, how much junk you lose. Also related to that is the half-life, because it's, you know, rate constants are typically really, really small numbers. So it's easier for us to think about half-lives. So like if I say the half-life of something is 1 day, it means that if I start with 100% of sample in 1 day, how much stuff do I have left? 50%. So it's easier to kind of communicate how long something lasts in terms of half-life. And so this is the equation for half-life for a first order reaction. This is all review. And so that number 0.693, it's not arbitrary. That number is actually natural log of 2. All right. It's not an arbitrary number. All right, so yeah, first order kinetics. And here's the other way to calculate mass remaining in a sample. If you know how many half-lives have passed, you can apply that to like the 50% rule to figure out how much sample you have left. So if my half-life is 1 day, but 2 days goes by, how much sample do I have left? What percent do I have left? 25%, yeah, because you take 50%, 50% again, 2 days, that's 25%. All right, so let's do calculations because this all is review. These are the equations and you do get these two. Okay, so we have 100 grams of radioactive sample. It undergoes 1 half-life. How much sample is left? 50 grams, yes. What if 2 half-lives go by? 25 grams, yes. And then 3 half-lives? 12.5, perfect. Okay, so what we did is we just, you know, cut it in half each time, right? But the thing is that like we rarely have half-lives that happen in just like even numbers or like integer values. So that's why we need the integrated rate law. If I know the half-life and I know exactly how much time has elapsed, I can use the integrated rate law to calculate how much stuff I have left. So let's say we have a radioactive substance with 48 grams. After 60 hours, 3 grams of sample is left. What is the half-life for this substance? So this is interesting. Okay, I went from 48 to 3. I didn't lose half of my sample. I lost more than half. So directly going to half-life is not useful here. What I actually want to do is calculate K, our rate constant, for that process. I know the time, I know the initial, and I know how much I have left. So this I can plug into the integrated rate law, get K, and then from K I can get the half-life. So let's remind ourselves what the integrated rate law is. So natural log of the stuff I have left equals natural log of my initial stuff minus KT. So looking at the information here, 48 grams, that is my initial concentration. 3 grams, that's my concentration at some time, and time is 160 hours. So I just plug in all those values to calculate what is K, my rate constant. So natural log of 3 grams equals natural log of 48 grams minus K, that's what I'm solving for, times T, 160 hours. All right, and so what we get here is that K is equal to, dang it, I didn't write it down. Okay, natural log 48 minus natural log of 48. Oh my gosh, natural log of 48 minus natural log of 3 divided by 160. So I get K is 0.0173 hours to the -1. Okay, that's K. That's what would be in your rate law. But that's not what the question asks. I'm not asking for K. I'm asking for half-life. So I need to go one step further and insert that in my T1/2 equation. So T1/2 equals natural log of 2 over K. And so when you plug in that K value, we get the half-life is 40 hours. All right, so natural log of 2 over 0.0, so let me check it. Natural log of 2 over that number is, yes, 40 hours. All right, and that, make sure that number makes sense numerically. Okay, remember what 40 hours a half-life means, that you'll lose your 50% of your sample in 40 hours. But the time that's given, is it more than one half-life? Yes, it is. But did we lose more than one sample? Yes, we did. So make sure that your answers kind of make sense in that regard. All right, and one other way you could do this is you could take this rate constant and plug it into the integrated rate law again, where you say that your initial concentration is 100%, and you could say your concentration at some time is 50%, and you could calculate T. And that's the same answer. You would get the exact same answer because the T1/2 equation is the integrated rate law with those numbers in it, 100% and 50%. It's the same idea. All right. Okay, let's do another one. The half-life of radium is that if Marie Curie isolated 0.21 grams of radium in 1902 and left it in her lab for 120 years, so up until now, so like 2022, I wrote this question last year, so 2022, how much sample is left? All right, so if 120 years elapsed, has a whole half-life gone by yet? No. So don't try to use the half-life equation. Just use the integrated rate law. But the problem is can we put a half-life value in the integrated rate law? No, I need to actually get K first, which I can get. 1,500 years, that's my T1/2. So I can just plug that into my K, into the T1/2 equation to calculate what K is, and then put it into the integrated rate law. So K is equal to natural log of 2 over that 1,500 years. All right, and so what we get is that K, the rate constant for that given half-life, is 4.36 times 10 to the -4 years to the -1. So that's K, and that's what we'll plug into the integrated rate law. But now the other pieces of information that need to go into the integrated rate law are the other pieces of information in the question. So what is this 0.21 grams? Is that my initial concentration or a concentration at some time? That would be initial, so 0.21 grams. We are calculating the concentration at some time, or the amount left at some time. So 120 years, to me, that sounds like T. All right, so it looks like we have all the information we need. So let's remind ourselves the integrated rate law, so natural log of concentration at some time equals natural log of initial minus KT. So natural log of, that's what I'm solving for, concentration at some time, equals natural log of 0.21 grams minus that K that I got. Again, don't just put in your T1/2. So 4.36 times 10 to the -4 years to the -1 times the time that is actually elapsed, and that's 120 years. All right. And so when you solve for that, so natural log of 0.21 minus 4.36 e to the -4 times 120. Why is Reddit saying stuff to me? I get that natural log of the concentration of stuff at some time is negative 1.613. And so if I E both sides, so E to that number, I get that the concentration left is 0.1993 grams. Oh, yeah, I have the answer right there. Great. But let's just check our intuition. Does that answer make sense? Yes, it does. Why? Because you lost some. Okay? Did you lose half? No, because a whole half-life hasn't gone by. So again, make sure that they all make sense there. All right, so I can ask a question this way. Okay, a sample lost 62% of its mass in 12 hours. What is the half-life of the sample? All right, so if we're talking percentages here, a good assumption to make is that my initial concentration is 100%. So then what is my concentration left at some time? Is it 62%? No. What is it? It's actually 38%, right? 38.9%, is that right? Yes? Okay. Yeah, so do understand, is that not right? 37, thank you. 37.9%. Do you understand the language, all right? You lost 60 whatever percent. So that in order to use the integrated rate law, it's how much is left at some time. So it would be 37.9%. All right, so I hope you see the direction here. 12 hours, that's gonna be your T. So don't try to plug these numbers straight into the T1/2 equation because it is asking for half-life. We need to put it into the integrated rate law first, get K, then get our T1/2. So let's put that together. Natural log of 37.9 equals natural log of 100 minus K times 12 hours. All right, and so then we get K is equal to 0.0809 hours to the -1, and then we can plug that into our T1/2 equation. T1/2 equals natural log of 2 over 0.0809 hours to the -1. Right, and so if you plug that in, you get T1/2 is about 8.5 hours. Does that answer make sense? Does it make sense? Does it? Okay, we lost 60% of our sample. So 12 hours, is that less than a half-life or more than a half-life? More than a half-life. So then when we calculate our half-life, it's a little bit less than what we observe. So 8 hours does make sense numerically. Okay, good. All right, so again, all radioactive decay processes follow first-order kinetics. All of this is just review of chapter 14 and using the integrated rate laws and our T1/2 equations, just in more detail. All right, so this is the last slide of just going over final exam material. Relating to half-lives, and if we think about in society, when we think about half-lives, oftentimes radiocarbon dating comes into mind. It's how we measure how old substances are, not substances, once living substances, right? Because carbon-14 occurs naturally in our Earth, right? When we eat, we are carbon-based beings, right? There's tons of carbon in us. We eat other carbon-based either plants or animals. So we always have this steady amount of carbon-14 in our bodies, all living things. We all have the same proportion of carbon-14 in our bodies. But we already calculated carbon-14 is not a stable nuclei. It does undergo decay processes, right? And it follows first-order kinetics. So the half-life of carbon-14 is about 5,000 whatever years, right? So this is what happens. Once we are no longer living and we're not eating and replenishing our carbon-14, we don't replenish our carbon-14, and so then it starts to decay. So if you just dig up, something that was once living and now is not living, it will have less carbon-14 in it. And so if we compare the amount of carbon-14 in the dead thing versus alive things, we can tell by the half-life how old things are. So that's how carbon dating works. The big idea is once you die, you don't replenish your carbon-14 and it starts to decay. But it just follows first-order kinetics as well. So if I ask the rate constant of carbon-14 and I give you the half-life, Now, yes, you can plug it into the T1/2 equation, but I don't want to do that. I want to use the integrated rate law instead, okay, just for fun. So remember what half-life means. You start with 100% and you lose, or you get to 50%. And so I'm calculating K, I give you T, the time it takes to go from 100% to 50%. So I'm trying to say that the T1/2 equation is the integrated rate law. So putting this all together, you would just do natural log of 50 equals natural log of 100 minus K, that's what we're solving for, times the time it takes that to happen. So 5,715 years. All right, and so when you solve for K, you get that the rate constant is this tiny number, right, in the corner there. And again, when talking about radioactive substances, it's easier to just say half-lives. It's nicer to read 5,000 years versus that tiny rate constant, because that 5,000 years kind of gives us an idea of how long that stuff sticks around. Oh, we'll lose about 50% of the stuff in 5,000 years versus that rate constant, which doesn't kind of lend itself to radioactive dating, all right? And so again, the equation with the integrated rate law, it's the same exact work if I would have done T1/2 equals natural log of 2, which is 0.693 over 5,000, oh no, I'm solving for K here. So K equals 0.693 over 5,715 years. You will get the exact same number. So prove it to yourself. Okay. So putting it all together, right? Carbon-14 is not stable, so let's prove it. Let's calculate the neutron to proton ratio of carbon-14. How many protons are on carbon? 6. How many neutrons on carbon-14? 8. So that's a N to P ratio of 1.33. So is that stable? No. All right. So then here's another question. So does that mean carbon-14 decays into carbon-12, or does it decay into something else? Something else, yes, because what does 1.33, our neutron to proton ratio, what does that imply has to happen? Yeah, beta emission? Yeah, beta emission. So a beta particle is 0 and -1. So let's draw it out. So we have carbon-14, so 14 there, 6 there. We get a beta particle. What's my product? 14, 7. What is that? Nitrogen. Yes. Is that nitrogen stable? Yes, it is. It has a neutron to proton ratio of 1. So yes, the answer here is something else, and specifically it is nitrogen. And I feel like that's not super intuitive. You would think, oh, carbon-14, it decays to carbon-12. Nope, it doesn't. It doesn't. It just becomes nitrogen. All right. So there we go. All right. And so that concludes all of Chem 1220 material. That's on the final. But I want to just take a really quick amount of time. We only have like 15 minutes left, and I need to do my demos and stuff and my inspiration. All right. And that's talk about nuclear reactions, okay? Nuclear energy, and maybe dispel any myths that are there. We utilize nuclear reactions to fuel nuclear energy and all those things. So where does that energy come from? All right, we burn coal, we burn gasoline to get energy, right? Those reactions are exothermic. Some nuclear reactions are also exothermic, but kind of for a different reason. And it's because of, do we all know this equation, E equals mc squared? Yep. So that Einstein equation is the consequence of where that energy comes from in nuclear reactions, right? Nuclear reactions are really high energy reactions. And what Einstein's equation says is that energy is equal to mass times the speed of light squared. So if energy is produced in a reaction, there's actually a little bit of mass lost in a reaction as well. All right, because he's equating energy is mass, and it is, and we can prove it to you through some inspections of the weights of our products and reactants. So in nuclear reactions, there is significant mass loss of our products and reactants, and that difference, that mass defect is where all of that energy comes from. So the idea here is, do all exothermic reactions have mass loss? Yes. When we burn gasoline in our car, right? If we actually, like, if we had a really, really expensive balance and was able to measure both sides, like our products and reactants, there is a tiny bit of mass loss, but just not enough to make a big difference. But in nuclear reactions, since tons of energy is produced, there is significant mass loss. All right, so here's an example of the alpha decay of uranium. If I took the masses of the products and reactants, do they match? No, they don't. They don't match. So we actually, did this sample lose mass or gain mass? It lost mass, all right? So this loss of mass, we call this the mass defect, is related to the energy that is released in this reaction, right? That mass loss via Einstein's equation, where he said that E equals mc squared. And so that delta M is related to the energy that's involved in that reaction. All right, so although this isn't on your exam, I think there are a couple homework questions about this, so it's important. Yes. All right, and so I calculated here the mass loss of this reaction is just a tiny, tiny bit. And so this delta M goes into our E equals mc squared equation. But because we want energy in a joule, and this is in AMU per atom, just convert it to grams per mole. But can we put a gram in and get a joule? No, we need to convert it into kilojoules. So I think on the online homework question, the big idea there is you need to convert that mass loss into kilojoules in order to get the unit of joules out. Or sorry, kilograms. Convert grams into kilograms to get a kilojoule. Our joules out for our equals mc squared equation. So we see a mole worth of this reaction will release this much energy, 4.13, so tons of energy, right? Just from that tiny, tiny bit of mass loss. And that's what happens in nuclear reactions, right? And so we see that heat is a product, and so that is related to the mass lost in the reaction. So let's think about that in reverse. Uranium breaks apart. It loses some mass. Let's think about a helium atom. All right, it's a nice compact helium atom. It takes a lot of energy to separate the components of a helium atom. So we're putting energy into a helium atom to get it to split apart into protons and neutrons. So let's compare the sums of masses on each side. Do they match? No, they don't. That the reactants are actually a little bit lighter than the products, and that's because you're adding a lot of energy to get this to split. So again, that energy is related to the mass defect, the amount of mass. That energy is related to mass in order to get them to split apart. And so this is specifically called the binding energy, the amount of energy required to split that helium atom apart. All right, so if we split this helium atom apart and it requires energy, what if we were talking about the reverse reaction? What if I took protons and neutrons, smashed them together to get a helium atom? Would that be an endothermic or exothermic reaction? Exo, yeah, because it's just the reverse reaction, right? And that's what fusion is. That's what happens on our sun. All right, so putting those ideas together, when we smash together small atoms and we get energy out, that's fusion, all right? Taking small things, making bigger things, that's how we get energy out, that's fusion. But the thing is, some bigger atoms, it's actually more energetically favorable to turn big things into small things. That's the uranium. Uranium decays and loses mass, it emits energy. So it's exothermic when big things split into small things. That's fission. That's what happens in nuclear reactors. All right. So what we see from this graph is that these elements tend to undergo fusion. Heavier elements tend to undergo fission. All right, so let's talk about that. All right, nuclear fission. This is what happens in nuclear reactors. All right, we're taking advantage of the fact that uranium decays, it loses a little bit of mass and releases a ton of energy that we can harness for our electrical needs, right? So this is how nuclear reactors work. We take uranium, the unstable one, we throw a neutron at it to initiate the decay chain. And so what happens is a couple of reactions can happen. It can decay into these substances or these substances, but the big idea is that tons of heat is released in the process. Right? And so kind of, the drawback of nuclear fission is that these substances, the products, are also radioactive. So they stick around for a long time. So that's one of the drawbacks, that the products are radioactive and they need to be disposed of properly. So we have heat, we have radioactive stuff. What else is a product here? Neutrons, okay? So if you have a bunch of neutrons being produced, can't those neutrons then go and initiate more uranium reactions? And this is how nuclear energy, nuclear reactors, that's how they can get out of control. If you do not control the number of neutrons floating around, high energy neutrons, then it can initiate more and more reactions. You have a positive feedback loop, all right? And that's how nuclear reactors can get out of control. And so the big idea, one of the worst partial meltdowns in United States history is the partial meltdown of 3 Mile Island, which is 30 minutes from my childhood home. But they've decommissioned it, so it's no longer operational. But I think I'll explain in this slide how the meltdown happened. So how do we take that energy from this reaction and turn it into electricity? We can't just take this directly and turn it into electricity. So what happens is we take that heat from the reaction, we heat up water to steam, and that steam turns a turbine. That's it. So really, nuclear energy, it just spins a turbine just like solar, wind power or hydroelectric power. It's no different in that regard. And so if you look at this picture here, all of the nuclear waste and nuclear reactions are in this closed loop, where there's another loop of water that gets heated and spins the turbine. And then there's another loop that's typically connected to the river stream to cool down the steam that's being produced. So never is the radioactive reaction happening in open air. It's always in a closed loop. And so what we see here are in our reactor core are control rods that are made of other substances that can absorb neutrons and control the rate of the reaction. So those control rods, if you lower them down, they absorb neutrons so you can slow down the reaction. So why 3 Mile Island and that partial meltdown happened is that one of the pumps in the secondary loop, this water loop, failed, right? So no water was getting into touching the reactor, all right? And so then the reactor just started overheating because there was no water loop that was being heated, all right? Yeah, so that's why the partial meltdown happened, all right? And so again, trying to dispel myths and stuff, again, the radioactive materials are never in contact with actual water, our water system. So I like to talk about The Simpsons and stuff because it's my namesake. When we look at these billowing cooling towers, and there's an episode of The Simpsons where Homer walks towards his work or his former workplace. So in this episode, he's walking towards the cooling towers. It starts raining and his jacket dissolves. They were trying to indicate that the smoke or the exhaust from the cooling towers was acidic or something. But the thing is what's coming off of those cooling towers? What is that? It's just steam. Yeah, and so this is really actually not true. All right, so there's just dispelling a little bit of a myth that this is just steam. That never is radioactive material in contact with our water systems. They're always in closed loops. All right, so there we go, dispelling that myth. All right, so that's fission, taking bigs to smalls. The smalls are radioactive, that's why it's bad. Okay, and that's why there's, apprehensiveness with nuclear energy. But so an attractive alternative would be fusion instead. So taking small things, turning it into big things, because that also releases energy. So if we smash atoms together like our sun does and make helium, we can take that energy. It's still nuclear energy, but the attractive thing is that the products are not radioactive. All we make is helium, and helium is abundant on our Earth. But the problem is with nuclear fusion, so smalls to big, is that the lowest temperature fusion will actually occur is 40 million Kelvin. All right, so it's hot enough to do it on the sun, but not on Earth yet, but we're getting close. There was a breakthrough just recently in December where scientists were able to get a fusion reaction to happen on Earth. They used lasers. And they shot it at a sample of hydrogen, and they made helium. And so they calculated the amount of energy that they put into the reaction was actually less than the energy that came out. Yes, but some of me and my laser friends, we were complaining about it because we don't know in their calculation. It takes energy to generate a laser, all right? So we don't know if they use that in their calculation. But I think in our lifetime, fusion energy might be a viable thing, and it's attractive because the products are not radioactive, yes. But it's still nuclear energy, all right? Nuclear fusion in stars. Okay, so our sun does fusion, all right? All stars do fusion. And so the difference between like red stars, blue stars, red giants, blue giants is the amount of fusion that takes place. So I think that's kind of interesting here. Our sun, which is a yellow dwarf star, all of these stars do fusion, but what we see are these different sequences, and it relates to the extent of fusion that happens in these stars. So our sun, we are right here on this graph, and this is, scientists put together all of the stars that we see in our galaxy, all have differing extents of fusion happening. When a star dies, right? When like a supernova, a star dies or whatever, it's because it's run out of fuel. It ran out of hydrogen in order to initiate fusion to occur. Or, stars will undergo the dying sequence once the temperature is not high enough to keep fusion going. All right, and so if you're into stars, I just really glossed over it really quickly here, but yeah, that's where it is. Okay, and the last one is bombs. So this is the very last slide that I'm going to talk about is bombs. And again, to maybe just dispel myths, all right? So there have only ever been 2 nuclear weapons that have been used in warfare, okay, on this planet, and both of them were dropped by the United States, unfortunately, but both of them were fission bombs. So you might hear terms like A bomb, H bomb. So that stands for atomic bomb and hydrogen bomb. So the bombs that we dropped on Hiroshima and Nagasaki, those were atomic bombs. Those were fission reactions, all right? So a fission atomic bomb just contains uranium, all right, just like in a nuclear reactor in a nuclear power plant. So in order to initiate it, they have to set off a ton of TNT in order to get the bomb to initiate, all right? So that's fission, all right? And there's a lot of nuclear waste aftermath with that as well. That is an atomic bomb, that's fission, all right? But even more powerful bombs would be fusion-based bombs, so hydrogen bombs, right? So hydrogen bombs do exist, but they've never been used in warfare, but they have been tested. So the power of a hydrogen bomb is extreme. And here's one of the reasons. A hydrogen bomb, in order for fusion to occur, the temperature has to be crazy high, right? So in order to get the temperature crazy high, they have to use a fission reaction to initiate it. All right, so it's like a bomb within a bomb. And then to initiate the fission reaction, they have to set off a ton of TNT. So it's essentially 3 bombs in one is a hydrogen bomb in order to get that fusion reaction to happen at all. But in any case, atomic bombs, hydrogen bombs, they're still nuclear weapons. It's still using nuclear transmutations here, but there is a distinction. There is a distinction. So they often call hydrogen bombs thermonuclear bombs, all right? And so the United States has dropped hydrogen bombs in testing forms, and so that would be called the Mike test that they did in 1952. And just to put it into perspective, 9 countries have atomic bombs. That's the fission one, uranium. Of those, 4 or 5 countries have hydrogen bombs, but no one has used them other than testing in warfare. All right, so there we go. All right, got 1 minute left. All right. I don't have that much, inspirational things to say, trying to think of it, but I will set these balloons off. This has been a great journey, and I'm privileged that you've allowed me to be part of one of your chapters in your academic pursuits. And I really hope that you take the skills and strategies that you learned in this class into the next step of your academic career. And so I guess the inspirational thing that I want to say is, take this time in your undergraduate career to explore. Are you recording me? Oh my gosh. All right. To explore and, find your purpose. Be prideful and proud of as you walk through these great halls, and just be genuine to yourself. Because when you're genuine to yourself, then you do great work. I feel like I'm like evidence of that. I come up here every day and profess my love of chemistry, but I wake up every morning at 5:30 and feed the chickens and the ducks, and I still draw on a razor sharp cat eye every morning, and I'm still here. And so to exceed expectations that society puts on you, like as a scientist, they put us into a box as scientists, but you can still be creative as a scientist. You can be a woman, but not enjoy the company of children, and that's okay. And so as long as you stay genuine to yourself, then you'll do great things, and I hope that you take that with you as you move along in your academic career. So now let's blow some stuff up, all right? Yay, okay. So we talked about nuclear reactions, but we're gonna go back into the realm of electrons, unfortunately. Yes, so, okay, let's blow this up. Okay, let's go. So remember the ears thing? Sorry I went over a little bit. Let's turn off the lights. Let's turn off the lights. Okay. All right, remember everybody. Remember everyone, the ears thing. Oh, and I just wanted to say, they put scientists in box, and oftentimes they think of scientists, they have a certain malice within society. They think scientists, chemists, they're evil, Snape or Walter White from whatever. But I hope that I'm part of the change that chemists can be good, kind of like Honey Lemon from what's that? The Big Hero 6. Yeah, there you go. All right. So, okay, let's go. So there's 4 of them. Okay, ears, everyone. I don't want to be the reason for your tinnitus. Okay, so 4 of them. Jeez. Okay, 1. Oh, no. Okay, so unfortunately, these are not nuclear reactions. Ooh. Jeez. Okay, last one. Okay. All right. Good luck on your finals, everyone. All right, see you at the review session on Tuesday. Okay. Where's my block of wood? Where is it? Where's my block of wood? Where'd it go? Oh no! Did we lose it? Well, it's over there? Okay. If you want to sign it, I'll have it up here.
Dr. I have one question.
Yeah.
So the energy